A deep dive into scikit-learn's ElasticNet combining the best of L1 and L2 regularization. ElasticNet is a linear regression model that leverages the strengths of both L1 lasso and L2 ridge regularization techniques. It offers a powerful and flexible approach to address challenges like overfitting, multicollinearity, and feature selection in linear models. Let's break down the details of ElasticNet, exploring its core concepts, key parameters, advantages, and limitations. Core concept: ElasticNet combines L1 and L2 regularization to achieve a balance between sparsity L1 and stability L2. L1 regularization lasso: it shrinks less important features coefficients towards zero, effectively performing feature selection. This helps prevent overfitting and improves model interpretability. L2 regularization ridge: it shrinks all coefficients towards zero but without forcing them to become exactly zero. This adds stability to the model and mitigates the impact of multicollinearity. Highly correlated features. ElasticNet, by blending these two techniques, allows you to control the sparsity of your model by adjusting the L1 ratio parameter. You can fine-tune the relative contributions of L1 and L2. A higher L1 ratio emphasizes L1 regularization, leading to more sparse solutions. Handle multicollinearity: the L2 component provides stability, making the model less sensitive to high correlations between features. Key parameters. Let's delve into the important parameters of the ElasticNet class in scikit-learn, along with their descriptions and default values. Alpha float. Default 1.0. This parameter controls the overall strength of regularization. A higher alpha value implies stronger regularization, leading to smaller coefficients and a simpler model. L1 ratio float. Default 0.5 determines the ratio of L1 regularization to the total regularization. A value of 0.5 default indicates equal contribution from L1 and L2. Setting it to 1.0 yields pure L1 lasso regularization, while 0.0 corresponds to pure L2 ridge regularization. Fit intercept bool. Default true specifies whether to calculate the intercept constant term of the model. Normalize bool. Default false indicates whether to normalize features during the fitting process. This helps in cases where features have vastly different scales. Precompute bool. Default false determines if the gram matrix dot product of the feature matrix should be precomputed. Precomputation can speed up fitting for large datasets with many features but requires more memory. Maxiter int. Default 1000 specifies the maximum number of iterations for the optimization algorithm to converge. Toll float. Default 1e-4. The tolerance for the stopping criterion of the optimization algorithm. Warm start bool. Default false if set to true. The solution from a previous fitting is used as a starting point for the current fit. This can be useful for iterative optimization or when adding new data. Positive bool. Default false indicates whether to force the coefficients to be non-negative. Random state int. Default none. This parameter controls the random number generator used in the optimization process. Setting a specific seed ensures reproducibility of results. Selection str. Default cyclic determines the strategy for selecting features during the regularization process. Cyclic selects features in a cyclic order. Random selects features randomly. Copix bool. Default true indicates whether to copy the input data before fitting. Verbose int. Default 0 controls the level of verbosity during the fitting process. Njobs int. Default none specifies the number of jobs to run in parallel for fitting and prediction. None uses all available processes. Attributes. The ElasticNet object provides several attributes after fitting the model. Estimated coefficients of the linear model. Intercept. The intercept constant term of the linear model. N features in number of features seen during fit. Feature names and names of features seen during fit. Niter number of iterations run by the optimization routine. Sparse representation of the coefficients. Methods. FitX. Y fits the model to the training data X and target values Y. PredictX makes predictions on new data X using the fitted model. Score X. Y calculates the coefficient of determination R2 of the prediction on data X and target values Y. GetParamSquargs returns the parameters of the estimator. SetParamSquargs sets the parameters of the estimator. Decision function X predicts confidence scores for samples X. SparseCoi gets the sparse representation of the coefficients. Advantages. Regularization. ElasticNet employs regularization, which helps to prevent overfitting and improve the model's generalization performance on unseen data. Feature selection. The L1 regularization component allows for automatic feature selection by shrinking the coefficients of less important features towards zero. Multicollinearity. Handling. The L2 component helps to mitigate the effects of multicollinearity, making the model more stable and reliable. Flexibility. The L1 ratio parameter provides flexibility in controlling the balance between sparsity and stability, enabling customization based on the specific problem. Disadvantages. Computational complexity. Fitting an ElasticNet model can be computationally expensive, especially for large datasets with many features. Hyperparameter tuning. Finding optimal values for alpha and L1 ratio often requires careful hyperparameter tuning through techniques like cross-validation. Interpretability. While ElasticNet offers some interpretability due to its feature selection capabilities, it may be less interpretable than simple linear regression. In summary, ElasticNet provides a versatile and effective approach to linear regression by combining L1 and L2 regularization. It addresses crucial challenges like overfitting and multicollinearity while offering feature selection capabilities. However, you should be aware of its computational cost and the need for hyperparameter tuning.